All right, welcome back for another episode of Business Calculus. My name is Scott Hayter. Let's see, we got section 1.2 here. It's linear functions. So let's get started. So first thing that we need to talk about is the average rate of change formula, also called the slope formula. So I think you've probably seen this before. So given 2 points on a graph, if you have two xy coordinates, then we can find the average rate of change, also called the slope, between the 2 points using the slope formula. So here's the slope formula. It has some different forms. First of all, we normally reserve m to be the slope, and we write the formula as y2 minus y1 over x2 minus x1. We can also write this formula as change in y over change in x. That's what this delta symbol means. It literally just means this. And there's another form you may have heard, rise over run. You may have heard of rise over run being the slope as well. And so these are three different ways to think about the slope, but they're all basically the same. Normally we use this, but later on we might kind of use a version of this one, slightly modified. But we need them all. We need all the formulas, depending on the circumstance. All right, so that's the slope formula. So make sure you're good on that. Make sure you have your y's on top and the x's on bottom. And as a note here, because you're going to need to assign units for every number that you calculate in this class. So if you calculate, I don't know, last video we calculated the concentration of carbon dioxide in the air. So the units in that case would be the parts per million. That's the units. Well, for a slope, the units will always be a fraction. Basically always. And the way you get it is you take the units of whatever the y value is measured in, and you divide by 1 unit of whatever the x is measured in. All right, so remember that. We'll be using it a lot. So that's whenever you find a slope or a rate of change, then you'll always have a fraction as the units for the number. Okay, so remember that. All right, good. So let's actually calculate a slope here. So here's an example. We have a graph, and the graph represents the distance traveled after t hours, and it says here distance is in miles and times measured in hours. So if we pick 2 points on this graph, we could find the average rate of change between those 2 points. So between t equals 2 and t equals 4, if we want to find the slope, remember we almost always use m for that. We'll take y2 minus y1 over x2 minus x1. These the y and x coordinate correspond both to t equals 4 and so forth. Okay, so what is d of 4? We need to read that off the graph. So that's the y value when x equals 4. So I go to x equals 4. I find my graph, and my y value is about 500. It's in between 400 and 600. So I put in 500 there. And d of 2, that is about 400. It looks to be exactly 400 by the way it's graphed. So I just put that in. And then I go ahead and calculate this number. So I get 100 over 2, which is 50. And the way I write my units is the units over what the y value is measured in, which is miles, and 1 unit of whatever the x value is measured in. All right, so it's 50 miles per 1 hour or miles per hour. We can just, it's a fraction, but we just write it as mph, of course. All right, so that's an example of how to find the average rate of change. Make sure you remember your units, get full points. All right, so now that we've talked about slope, we're ready to talk about linear functions, because linear functions are defined as functions where the slope is constant. Okay, that's a characterization of linear functions. So no matter what 2 points you choose, when you find the slope between those 2 points, you get the same number. You get the same relationship. All right, so for example, this is an example of a linear function. And when we graph it, it looks like, shocker, a line. Okay, so it's a good name for this type of function. And the equation, the formula for linear functions always looks like this: y equals mx plus b. This is how I always write it, at least. And we use m for the slope, and b, I usually write in b there for the y-intercept. It's the function evaluated when x equals 0. It's the y value when x equals 0. Notice on the y-axis, x value is always 0. And so where we have a graph there, that's the y value of the function when x equals 0. It's called the y-intercept. All right, so make sure you're clear on all that. Let me just say something before we move on. So linear functions are they're about the simplest type of function that we can analyze. But they don't really occur in nature so much. When we try to use functions to understand this world better by describing relationships quantitatively, we use functions to do that. And we don't see linear functions occurring all that often. It's just most things in nature don't change linearly. They're more like sort of exponential in nature, which we'll talk about later. But, however, if we understand linear functions very well, then we can kind of reduce complicated functions. If we want to understand a very complicated function that's not a linear function, we can kind of reduce it down to a line. We can kind of use our insight about lines to understand it better. So this is true for all levels of math. Up to very high levels of math, basically what mathematicians do is take very complicated functions and they use their insight about linear functions to answer questions about the complicated function. So even though it doesn't occur that often in nature, it's still very insightful and useful, but we need to understand it very well. Okay, so that's my spiel about that. Let's move on. So a fundamental skill that you'll need in working with linear equations is to be able to construct the equation or the formula given 2 points. So if you're given 2 points on a line, you need to be able to come up with the equation for the line, the function. We know it's going to look like f of x equals mx plus b. And the first thing that we should do is find what m is, what the slope is. So that is y2 minus y1 over x2 minus x1. I will just plug them in my formula here. And I'll calculate that through. 14 minus 2, that's 12. 5 minus a negative 1, that's 5 plus 1, which is 6. And that's 2. Make sure you're good, or I shouldn't say make sure you're good. Make sure you're careful about when working with negative signs, because I myself have spent a long time in graduate school trying to find a mistake that I made involving a negative sign. Basically, I added when I should have subtracted, or subtracted when I should have added, or something like that. So I would guess that you'll probably run into that at some point as well. You'll be confused about why your answer is wrong. And just be very careful about what you did with negative signs, because that can throw everything completely off, of course. It's an easy mistake to make. Okay, so we know the function looks like y equals mx plus b, and now we know m. We know m, so we just put that in. We don't know what b is yet. Okay, so that's what you should do first. Now when you want to find b, you can just plug in an xy coordinate. So if you look at this equation, it's like we have 3 variables. your y, your x, and your b. Three things that we don't know. But if I plug in an x and a y, then I'll only have this thing that I don't know, and so I can solve for it. If I got an equation with only one variable, I can solve for that. So let's do that. So I'm going to plug in the point -1, 2. And so I'm going to put -1 in for x, I'm going to put 2 in for y, and I'm going to just evaluate that and simplify that and solve the equation for the only remaining thing that I don't know, which is b. And I got b equals 4. So I no longer need to write b in my equation, I can write 4. All right, so this is a simple process, but it's something that you need to know very well for reasons that I explained earlier. One quick note, while I'm just throwing everything about linear functions at you, is that why do we do y2 minus y1 instead of y1 minus y2? Because 1 comes before 2. Why don't we write that first? Of course. Well, we write y2 minus y1 because that represents the change from y1 to from y1 to y2. So for example, if I have the number 1 and I change that to the number 5, I've added 4 to that number, going from 1 to 5. The way I get that change is by taking 5 minus 1. So the second coordinate minus the first coordinate. So that's why we write it like that. Technically, it would be the same if you wrote f of x1 minus f of x2, as long as you write x1 minus x2 on bottom. But the difference is in how we're thinking about it. It's not clear why you would write that, because that would be negative change in y. And even though the negative signs cancel out, it makes it unclear to perhaps a reader of your work why you wrote it like that. Anyways, so that's that. I think that's about all the spiels I have for the lecture. We'll see though. Maybe I'll come up with more. Okay. So, like I said, we need to understand linear functions very well. Even though they're simple functions, we need to be patient and try to understand exactly what it's telling us as much as we can. So what does this slope actually mean? So literally it means that it's the change in the y variable as we increase x by 1. Okay, that's key. That's key. As we increase x by 1. So if the slope is 3, that means that if I add 1 to the x value, then I need to add 3 to the y value. So if I go from 5 to 6, then I need to go from 7 to 10. All right? Now, this is useful even if we are not adding a whole number to x. So what if I'm adding like a half to x? Well, instead of adding the slope, I'm just going to add half of the slope, right? Because that ratio is fixed. So instead of adding 3, I'll add half of 3, which is 1.5. And 7 plus 1.5, that's 8.5. All right, so that's another point on this graph. So remember that. And what if the slope's negative? Well, the slope tells us how much the y value changes, and if it changes by a negative amount, then that means it's decreasing, right? So we just subtract. We subtract. So if we start with 5, 7, and we add 1 to x, we must subtract 3 from y. Right? So that's literally what the slope means. Okay, so that's that. And our last example here is suppose we have we're given a function that represents the revenue for McDonald's between 2013 and 2015. It's a linear function. Capital R represents the revenue. Usually capital R is used for revenue. We'll see that a lot. And we look and see that it's defined in billions of dollars. And last time we talked about how t is usually defined as years since something. So t is, in this case, it's years since the beginning of January 13. Okay, so let's see. What is the slope of this function? So the slope is the coefficient to the x variable, which is t in this case. So the slope would be minus 1.35. It's just that number. All right, so, and what does that number mean? So it's minus 1.35. I guess before talking about the meaning, let's talk about the units real quick. So remember how we get the units. We take the units of the y variable over the units of the x variable. So that the y variable revenue is measured in billions of dollars. So we put the dollar sign in front, so billions of dollars, and then we divide by the x variable, years. But remember, we just divide by 1 unit of the x variable, so it's just 1 year. So so get good at writing the units for each number. So negative $1.35 billion a year. This means that each year the revenue decreased because it changed by a negative amount. It decreased by $1.35 billion. We wouldn't say that it decreased by a negative 1.35 billion because after we say decreased, we've already taken into account that negative sign. Okay, so that's the slope of the function, and that's what it means. Another question would be, what's the y-intercept, and what does that mean? Well, this is our slope, that other number without the variable, that's the y-intercept. So that's 28.1. What would we measure 28.1 in? Let's see. What does it represent? It represents the initial value of the function. So should we also measure that the same way that we measure the function in? And the answer is yes. So what's the function? The function is revenue, and that's measured in billions of dollars. And so that's how we measure the y-intercept. It's also in billions of dollars. Y-intercept is not a fraction, like the slope. So this is the initial value, we say. And it's the revenue in 2013. It's the y value when x is 0, when t is 0, which corresponds to January 2013. All right, so that's that. One more question here. It says, when would the revenue be $18 billion? So whenever it asks when, I know that usually I'm asked for an x value, and it tells me the y value in this case. So instead of giving the x value and asking to calculate what the y value is by evaluating the formula, we're doing the opposite. So we're going to put in what it gives us for the y value, the revenue, and we're going to solve for the x value. Just like this. Just solve this equation. So I'm going to subtract 28.1 on both sides. And then I'm going to divide by minus 1.35. And I get this. And then I just got to remember what t means. T means the years since 2013. And so 7 years after 2013, that's 2020. So 0.48, that's like half. So it's like halfway into 2020. So it's in 2020. All right. So the answer would be in 2020 is when the revenue crossed $18 billion. All right. So that'll about wrap it up for linear functions. And yeah, so have a good day and good luck on your web assignment for this section.